Welcome to the next session, which spotlights innovations in cement and concrete technology. At WCA, we embrace not only cement producers, but also stakeholders in the wider industry. And we do this because we believe that including these stakeholders in our network is more relevant and more powerful in facing the challenge of climate change and decarbonization. So in the next session, we're going to hear from four different speakers, all with different approaches to the challenge of decarbonization. First up, we'll hear from Brent Constance, who's CEO and founder of Blue Planet. And then we'll hear from Christy Gamble, the Senior Director of Sustainability at Carbon Cure. Then we'll hear from Paul Mistrick, Director of Applied Research at Solidia Technologies. And then finally from Jerome Portal, who's Sales Manager for Mineral Products at FEEV FCB.
Hi, I'm Brent Constance, CEO of Blue Planet in California. I'm here today to talk about the role that concrete can play in fighting climate change. And what I'd like to communicate is that I think concrete can play a much, much larger role than simply curtailing the CO2 emissions from cement. The fact is that concrete, being the most used building material in the world and one of the most used commodities on Earth, has the capability to store gigaton levels of carbon dioxide in the matrix of the concrete in the form of carbonate minerals. And this presents a really important opportunity that is outside the realm of just cement. If we look at the history over the last few decades of how we've approached concrete and lowering the carbon footprint of concrete, we focused primarily, for good reason, on the cement sector itself, and with the goal of lowering the impact of cement on climate change. We believe that mankind puts out something on the order of 40 gigatons or 40 billion tons of CO2 a year. We believe that there's about 3 or 4 billion tons of Portland cement manufactured every year. And we believe it's responsible for 3 or 4 billion tons of CO2, 3 or 4 gigatons of CO2. Now that's far less than a tenth of all of anthropogenic CO2. So first we have to acknowledge the fact that even if we were to completely eliminate the carbon footprint associated with concrete, which is primarily associated with the cement, it would have some effect on climate change, but it would be less than a tenth of the total amount of CO2 that mankind's putting out. So while a laudable goal, the mere reduction of CO2 coming from cement used in concrete isn't going to solve the whole problem or even have a super significant impact compared to that of liquid transportation fuels or the production of electrical power. By contrast, the role that cement can play, and particularly the finished product concrete can play in sequestering CO2 from the other sectors is very significant. And when we look at the global problem, the problem is partially how do we capture all the carbon dioxide from industrial and transportation and power generation? How do we capture it? But then once captured, what do we do with it? Most climate change models indicate we need to mitigate or remove something on the order of 10 gigatons or more, even 20 gigatons of CO2 in the coming decade or so, to really be on track to meet the Paris Treaty and hopefully the treaty coming up in Glasgow. And we're not going to be able to do that simply by mitigating the CO2 coming from cement, which is only 3 or 4 gigatons, even if we were to mitigate it all. And what we do need to do, though, is we need to find a practical, economical means to capture CO2 from all the other sectors, including cement, but all the other industrial, steel, aluminum, blue hydrogen production, as well as power generation and liquid transportation fuels. So the mechanism that we have to work on with concrete principally has been simply figuring out ways to reduce the amount of Portland cement, which may account for 1 billion or maybe 2 billion tons of lowering the amount of carbon dioxide in the total human output. But if we could use the concrete to actually provide the location where we're storing the CO2, that provides a whole different dimension that's available to us. Just to note, technologically, while replacing cement with a new cement, and this is an area I've worked for over a decade, and I have over 100 patents in the area of cement, is a laudatory cause. There are many aspects of commercializing a new cement which are problematic. They have to do with shelf life. They have to do with codes that are developed around the world. We really need decades of experience with new cement and concrete before we're going to see broad commercialization. And we really have to think of new cement, a new type of cement, as sort of a 2040, 2050 reality in terms of broad commercial usage. We have a current methodology today that it can be applied today, which is capturing CO2 from cement kilns and mineralizing it and permanently sequestering it, or capturing CO2 from other sectors like other industrials or power or transportation, and also mineralizing it. And by mineralizing it, we form the other component of concrete, not the cement, but the aggregate, the sand and the gravel that is available in concrete for storage of CO2. And the aggregate in concrete consists of 80, 85, 90% of the total mass. There's over 50 billion tons of rock mined every year for use principally as aggregate. And the dominant form of aggregate use is limestone. Limestone is calcium carbonate, and the carbonate comes from CO2 in the calcium carbonate, and 44% of the mass of limestone is actually CO2. So if I have a ton of limestone, represented there is 440 kilograms of CO2 now permanently converted to CO3 in the crystalline state. So we now have the capability to capture CO2, convert it to carbonate, turn it into a calcium carbonate limestone, and use that limestone in concrete as in place of the mined aggregate. This provides the largest potential for the concrete industry to help fight climate change, is by acting not on the cement component, because the CO2 from the manufacture of cement can simply be captured and mineralized, but rather taking mineralized CO2 from all of the sectors, power, transportation, industrials, converting it into limestone, permanently sequestering it there, and then using it as the aggregate in concrete, which is the largest commodity in a marketed product, which has economic potential to fund the capture and sequestration of the CO2 in poor countries and rich countries around the world. Now, systems for demonstrating the value are being developed all over now. This, for example, is from San Francisco International Airport. And these are their guidelines that they're using for the further the development of the airport. And what they're doing is they've set out guidelines coming up over the coming decade of how the airport is going to achieve 50% emissions below 1990 base levels in both their operations and the material selections that they have. So for example, they have the typical LEED certification that you would use, but when it comes to the concrete, they're specifying the carbon intensity of the concrete here using the Carbon Star rating system, the new rating system for quantifying the energy intensity of concrete, which is auditable by a third party and a repeatable methodology for essentially an LCA on concrete. But here they are specifying concrete that's 200 pounds of CO2 per cubic yard, whereas a typical yard of concrete may be 600 pounds. They have stretch goals where they're seeking concrete that's 0 pounds per cubic yard, meaning carbon neutral in their build out. And even exceptional project goals where they have carbon negative concrete, where they've been able to sequester CO2, in this case using carbon sequestered aggregate, to make the concrete where we're storing the CO2. Now these systems are developing broadly now and will undoubtedly see a lot of traction in coming years. For instance, the Canadian Standard Association has recently issued the Carbon Star North American Technical Standard, which allows for the specification of the carbon intensity and how to quantify it and verify it. This allows governments to use their procurement of materials that have sequestered CO2 in them to quantify the amount of CO2 that will be sequestered. And this is where the concrete industry can really step in and make a difference, not only with understanding what the real carbon intensity is of concrete in a verifiable, validated method that's auditable by third parties, but also provide examples of how their leadership can lead the whole climate change community and provide significant guidance for how we're going to meet our goals in Glasgow. So with that, I'd like to say thank you very much, and it's been a real honor to be able to address this audience. Thank you very much.
Hello, everyone. My name is Christy Gamble. I'm the Senior Director of Sustainability with CarbonCure Technologies. It's my pleasure to join you today from Regina, Saskatchewan, Canada. Thank you for allowing us this opportunity to share our innovation for the cement and concrete industry, CO2 utilization for concrete. In today's presentation, I'll share a little bit about how CarbonCure technology works and where we're available. First of all, did you know that the World Green Building Council has begun its Advancing Net Zero campaign, which is bringing embodied carbon up front? In this campaign, the goal of the World Green Building Council is to reduce embodied carbon by 40% by the year 2030 and to eliminate embodied carbon by the year 2050. Now, embodied carbon is the carbon footprint of buildings before the lights are turned on for the first time. It's the carbon footprint that comes from building materials and construction. Concrete has the opportunity to be part of this solution. As the world's most abundant man-made material, concrete is one of the largest contributors to the built environment today. This also means that concrete has the ability to play one of the most impactful roles in achieving net zero embodied carbon. CarbonCure is working with the cement and concrete industry to help decarbonize the industry to meet these objectives. What exactly is CarbonCure? We are a CO2 utilization technology provider for concrete. CarbonCure's technology beneficially repurposes carbon dioxide as an admixture to reduce the carbon footprint of concrete without compromising the concrete's performance. A little bit of background information about CarbonCure. We were founded in Halifax, Canada in 2012 by Rob Niven, our CEO and founder. To date, our technology is in use at over 350 concrete plants across the globe. Most of this is within the United States. We are beginning our expansion to other parts of the globe, including Europe, Asia, and Australia. To date, over 8 million cubic meters of concrete have been produced using CarbonCure. Now, this concrete is being delivered to a wide range of construction projects, some of which I'll highlight, ranging from rural driveways through to large industrial warehouses and offices and highways. CarbonCure recently was named the Global Energy COSIA Carbon X Prize winner. This was a really prestigious competition that spanned over 5 years, in which the goal of the competition was to utilize CO2 to make valuable products. Our co-winner of this competition was also an innovator in concrete. And this really shows how much concrete has the ability to be part of this solution, the carbon solution through CO2 utilization. We're also very proud to be 2020 North American Company of the Year and to be backed by many fantastic and recognizable companies that are supporting our global expansion and supporting our company's success. Now, our mission is to reduce 500 megatons of carbon emissions annually by the year 2030. This is equivalent to taking 100 million cars off the road. In order to achieve this mission, we need the partnership of the cement and concrete industry. We're looking for a partnership with you. Getting into a little bit of detail about how the technology works, starting with the CO2 supply. So as I mentioned, CarbonCure's technology is introducing CO2 as an admixture. This CO2 is originally sourced from an industrial emitter. It is CO2 that would otherwise be a pollution. How it works is third-party companies, industrial gas suppliers who operate all across the globe today, collect and purify CO2 from emitters such as fertilizer and ethanol plants. That CO2 is then delivered to concrete plants. At every concrete plant where our technology is installed, the CO2 supplier will install a pressurized tank where the CO2 exists as a liquid. That CO2 supplier will then come by on a regular basis and refill that tank with CO2 as needed. Our technology is a precise metering and injection system. We are pulling that liquefied, purified CO2 from the pressurized tank and introducing a precise amount into the concrete as it's being mixed. This is all integrated with the batching software that exists at any given concrete plant, and it's delivering a precise dose based off of the particular batch of concrete that's being loaded at that moment. Now, this is happening at the same time as other processes in the batching sequence, and so it's not impacting the cycle time or the time that it takes to make the concrete. At the end of the day, really, from an operational perspective, it's exactly the same as introducing any other kind of admixture. Now, what happens when that CO2 is introduced into the concrete mix? A chemical reaction occurs where that CO2 finds calcium ions from the cement, and these two materials in the presence of water have almost this magnetic attraction to each other. They bind together and immediately begin to convert into calcium carbonate, which is essentially limestone. So we are turning what used to be a greenhouse gas into a mineral that now becomes permanently embedded in the concrete. What's even more important about this process is that this mineralization of the CO2 improves the concrete's compressive strength. The mechanism behind this is what's happening is we have this CO2 that's being introduced into the concrete and at a nanoscale is converting into these nano-sized calcium carbonate particles. And these nanoparticles are smaller than silica fume. They become embedded throughout the matrix of the concrete mix. These nanoparticles will bind to the cement grains and increase the surface area of the cement grain, making that cement more efficient. So with more efficient cement, that enables concrete producers to in turn engage in mix optimization. The CO2 has a neutral impact on the fresh and hardened properties of concrete. There have been many, many studies conducted by academics, by third-party organizations, such as in the United States, departments of transportation, that verify these statements that the fresh properties, the set time, workability, concrete pumping, air content, temperature finishing are unaffected by CO2. Hardened properties, freeze-thaw, pH, density, durability, color, texture, again, unaffected. In fact, some studies are indicating that there are certain durability properties that may be improved through the use of CO2. At the end of the day, the concrete that's delivered to construction sites meets the same quality and control standards, the same compressive strength, but with a reduced carbon footprint. The amount of carbon that can be reduced really depends on a number of factors. It's very mix specific. It's typically between 12 to 20 kilograms of CO2 per cubic meter can be reduced. This typically represents about a 5% reduction in the overall carbon footprint. Now, the CO2 is saved through both a combination of mineralizing CO2 and by optimizing the cement content in order to reduce further embodied carbon. As I mentioned, we've been utilized on a number of projects to date, primarily across the United States and Canada, some of which I'll highlight here. So everywhere from in Halifax, Nova Scotia, where we have lots of freeze-thaw conditions to consider. Here's an example of a hockey arena. You can see on the far right, again, another Canadian project. This is a de-icing apron with the Calgary airport. So on this particular project, it was 25,000 cubic meters of concrete supplied from a portable batch plant over the course of 8 weeks to deliver concrete paving used for airport tarmac. So as you can imagine, this was a very stringent application that required thorough engineering review, and we're very pleased to say that concrete was supplied successfully, and that airport is in use today and with great success. If you'd like to look at other parts across the North America, one of the buildings that I'd like to highlight is perhaps our marquee project currently underway in Arlington, Virginia, Amazon's headquarters. In this particular phase of the project alone, we expect to save over 1,250 tons of CO2. So this is very exciting to be aligned with mission-aligned organizations who are also working to reduce embodied carbon. And it should be noted that this is also being used in everyday kind of concrete applications. So while this really appeals to the Amazons of the world who are looking for solutions to reduce embodied carbon, it's accessible to the everyday concrete finishers and home developers who are building with concrete every single day. And I mentioned we have partners across the globe. So within North America in particular, we've certainly had our strong share of partnership and growth. We continue to grow on an exponential basis in terms of both the number of concrete producers who we've partnered with, as well as the cubic meters of concrete being supplied. And we are beginning to partner with producers in other parts of the globe. We're certainly interested in working with mission-aligned organizations who are looking for solutions to reduce embodied carbon and engage in best practices of mix optimization for concrete. So with that in mind, again, CarbonCure is on a mission to make concrete part of this climate solution. We truly believe that concrete is a fantastic material that can be part of the global solution to reduce carbon. So please reach out to us and join us. Thank you very much. Have a great day.
Hello, my name is Paul Meistrick. I'm Director of Applied Research at Solidia Technologies. Solidia is a technology company developing and commercializing low embodied carbon cement and concrete solutions for the precast and ready-mix industries. In this presentation, I'll present a pathway for significant industry-wide CO2 savings using Solidia's low-carbon cement. I'd like to start off by stating a major challenge that we, the cement industry, are faced with. Annual global production of roughly 3 gigatons of clinker emits about 2.5 gigatons of CO2. On a per-ton basis, that's 0.815 tons of CO2 emitted for every ton of clinker produced. Solidia has precast and ready-mix technology solutions that can significantly reduce these emissions while simultaneously providing additional value to producers and customers. Let's first take a look at Solidia cement and precast Solidia concrete. This photo shows a precast Solidia paver installation at our headquarters. Solidia cement is commercially produced both in the United States and Europe. It's produced using the same raw materials and the same equipment presently used for OPC production. The production of Solidia clinker emits about 30% less CO2 at the kiln when compared to OPC. Lower emissions are the result of the low limestone chemistry of Solidia cement, which requires lower kiln temperature, saving fuel, and less CO2 emitted from limestone calcination. A bar graph below illustrates savings between OPC clinker and Solidia clinker. Total savings for Solidia clinker production is 0.25 tons CO2 per ton of clinker relative to OPC. I should note that for both cements, I'm reporting emission numbers for clinker, and I'm not considering the addition of things like limestone or gypsum. One application of Solidia cement is in precast concrete. Solidia cement is a non-hydraulic cement. It cures by reacting with gas phase CO2. Unlike OPC, Solidia cement doesn't react with water. In the presence of CO2 and a small amount of water that serves as a solvent for the carbonation reaction, calcium silicates are converted to calcium carbonate and silica. The products are stable and impart excellent properties to the final product. During the carbonation reaction, up to 0.24 tons of CO2 are sequestered per ton of cement. This reaction is rapid and goes to completion in hours, not days like in the case of OPC. The waterfall chart at the bottom of this slide shows a comparison of the CO2 footprint of precast Solidia concrete to precast made with OPC concrete. Starting with OPC at the left with a 0.82 tons of CO2 footprint, there is a reduction in emissions as we switch to Solidia cement. We also include the emissions associated with the high purity CO2 supply that we are currently using, shown in orange. Roughly 200 kilograms CO2 emitted per ton of CO2 captured, liquefied, and transported to the end-use location. An additional reduction in footprint occurs due to CO2 sequestration during curing of Solidia concrete. Here we're using 0.24 tons of CO2 per ton of cement. This results in an emissions reduction of 0.44 tons of CO2 per ton of cement. I should note that the small parasitic losses occurring during the curing process are not included. We'll use this number, the 0.44, on the next slide to calculate the potential impact of this technology on industrial CO2 emissions. Solidia precast concrete is in the market today with paver and block production in North America and Europe. Our commercial production has demonstrated cost and performance advantages over OPC-based precast concrete. We've started with pavers and blocks because of the ease of entry afforded by manageable code requirements and have seen fast adoption both by producers and end users. The potential CO2 impact of precast Solidia concrete is large. Traditional precast represents 30% of the concrete market and consumes about 0.9 gigatons of cement annually. Converting 100% of the cement used in precast to Solidia cement would save up to 0.4 gigatons of CO2 annually. In this section, I'll talk about how Solidia cement, which reacts with gas phase CO2 to cure, can be used in ready-mix applications in a way that doesn't require CO2 gas for curing during end use and at the final end use site. One way that Solidia cement can be used in ready-mix applications is by using it to make a synthetic pozzolan, we refer to this as Solidia SEM, that can be added to OPC-based concrete. Like fly ash or slag, Solidia SEM can be used to replace up to 50% of OPC in concrete and has been shown to improve concrete performance. The box at the top of the slide shows our process for making 1 ton of Solidia SEM. 0.8 tons of powdered Solidia cement is reacted with 0.2 tons of CO2, in this case from flue gas, to create 1 ton of carbonated supplemental cementitious material, or SCM, in powdered form. I'd like to emphasize that CO2, which in this case is an industrial waste product, makes up 1/5 of the final mass of the product. This means that only 0.8 tons of cement are needed to make 1 ton of final product. The carbonation reaction for making Solidia SCM is the same reaction that occurs when precast Solidia concrete is made. Calcium silicate plus CO2 forms calcium carbonate and silica. The silica, which forms at the surface of the SCM particle, acts as a binder in the presence of OPC. Like precast Solidia concrete, Solidia SCM has a lower CO2 footprint than OPC-based products. The waterfall chart illustrates footprint reduction starting with our baseline 1 ton of OPC clinker, which emits 0.82 tons of CO2 at the kiln. As explained on the previous slide, less than a ton of Solidia cement is needed to make a ton of Solidia SCM. In this case, we need 0.8 tons of Solidia cement, which has a footprint a little more than half of OPC's footprint. A further reduction in footprint comes from sequestering 0.2 tons of flue gas CO2, bringing the final footprint of 0.82 down to 0.23 tons CO2 per ton of SCM, a total reduction of 0.59 metric tons of CO2. I should mention that we do not include parasitic process losses here, which are small relative to the overall savings. Solidia SCM is currently under development and will soon enter the market. We have already demonstrated this technology with pilot scale test pours, shown here in the photo, and have seen excellent performance both in terms of mixing, forming, and final properties. Evaluation and testing are underway at certified third-party and academic labs. Since Solidia SCM is used as a partial replacement for OPC, higher replacement levels lead to increased CO2 savings. We have demonstrated successful replacement levels up to and including 58%. The plot illustrates CO2 savings versus replacement level. Using the base case of 35% replacement level, CO2 footprint is reduced by 0.2 tons CO2 for every ton of blended OPC made with Solidia cement. Like precast concrete, the potential CO2 savings of Solidia SCM is large. Traditional ready mix represents 70% of the concrete market and consumes about 2.1 gigatons of clinker annually. Replacing 35% of the OPC cement used in ready mix with Solidia SCM would save up to 0.4 gigatons of CO2 annually. We started off this presentation with a major challenge facing the cement industry: 2.5 gigatons of CO2 emissions arising from the annual production of 3 gigatons of OPC clinker. Taking the 0.4 gigatons CO2 savings from both Solidia Precast and SCM gives a combined annual reduction in CO2 footprint of up to 0.8 gigatons. This represents a roughly 1/3 reduction in CO2 emissions and can be done with very little change to existing practices, equipment, or raw materials. I'd like to stop here and close by thanking you all for your time and attention, and hope to see some of you at the networking session.
Hi everybody, my name is Jérôme Portal and I am working with Fives FCB company in France. Today I would like to introduce you to the use of one of our flagship machine, the FCB Rodax 4D, in the field of concrete recycling. The construction sector is facing many challenges. 3 amongst them are to be noticed. First, the volume of wastes coming from demolition. In France, about 50% of these materials are recycled and 50% are buried. Buried material cannot catch CO2 and cannot be reused to make new concrete. Also, there are less and less permits delivered for the extraction of natural sands and gravels in order to preserve our environment. That's supposed to find a solution to substitute their resources. Cement plants are a significant contributor to the current CO2 emissions, 7% of the global CO2 emissions in fact, mainly because the process implies the decarbonation of limestone. New routes must be found to reduce the production of clinker. To face these 3 challenges, Fives achieved very promising results in recycling concrete with the FCB Rodax 4D. A Rodax is a vibrating cone crusher which has been developed in the early 90s. It has a cubic shape and the outer body is moved by means of 4 unbalanced masses, in purple covers in this picture. You will find a complete movie on YouTube and on our website to understand how it works. On the left-hand side, you have a figure of what happens in impact crushing. And on the right-hand side, you have the figure of what happens in compression grinding. Rodax is an interparticle crusher that works in bed combination, like FCB roller mill, vertical roller mill, and HPGR. Benefits in concrete application are to liberate the gravels from the mortar matrix and to get a very good particle shape. Also, the quantity of ultrafines generated can be controlled. Traditional impact crusher will produce smaller particles of concrete. A Rodax will separate the constituents of concrete due to the compression crushing, as you can see in this picture. Then, our vision is to answer the 3 challenges of construction sector in recycling aggregates, produce mechanical sand, and valorize the hydrated cement paste in the cement process. If these 3 routes can be put in place, then concrete could be 100% recyclable. One of the routes to valorize the fines is to put them in a raw mill mix at the cement kiln inlet. Without compromising the chemistry, up to 20% of raw mill can be replaced by the hydrated cement paste. The substitution could lead to a potential reduction of 6% of thermal consumption and 12% of CO2 emissions reduction. So, this route is an important means for cement producers to reduce their CO2 footprint. A very interesting route for the sand fraction is to catch CO2 and transform the hydrated cement paste in calcium carbonate. We obtain a defularized sand containing silica and limestone that can be used for both concrete and filler application. The industrial potential of CO2 capture is already about 50 kilos per ton of sand treated. The installation requires a jaw crusher in front to reduce the big blocks and to clean the concrete from plastics and rebars. Then, we feed the Rodax with the jaw crusher outlet and we run in closed circuit to produce different fractions. The Rodax is installed in a steel structure that can be easily moved from one site to another. Thank you for your attention. I can answer some questions, if any, through the Q&A tool. Many thanks.
So thanks for those fascinating insights. I think these approaches to making concrete and mineral, let me do that part again. Thanks for those fascinating insights from all 4 of you and illustrating the range of different options that we have to address the problem of decarbonization. I think from these presentations, we can also be somewhat optimistic about the potential. And of course, longer term, we'd like to see cement and concrete change from being a very substantial emitter to realizing its potential as a carbon sink. So you can now go to our networking lounges and speak to the presenters, ask them questions, and I encourage you to do that.